Hello, this is Bernard Brault. I always end up doing one video too many on pretty much all topics that I publish. But I promised I was not going to do another video on sea level rise, and here's my last one. And I think it's going to bore you out totally, except for a few of you that might recognize what's going on here and potentially could appreciate this. The odds of that are pretty low. So this is what I was doing when I look for sea level rise acceleration, and I'm looking here at the overall transfer function. So I had the raw data here that was provided by satellite measurement from the University of Colorado. I filtered the raw data, and I got a height, if you want, or a filtered height with removing some of the noise. And then in the calculation I did in the Excel spreadsheet is I took the derivative of this position and I got a velocity, and I filtered out the velocity because when you take a derivative you end up like amplifying high frequency noise. So I filtered it out, got a velocity or sea level rise rate, if you want, and then I applied more or less the same here, derivative of the velocity to get acceleration, and again filtering out the acceleration. And one thing I mentioned about all of this is that when you actually perform what's called a Laplace transform, which is instead of taking these derivatives and all that somehow is relatively hard to analyze, and what I did is did a Laplace transform, and the filter, I showed that the filters that I was using as a transfer function of 1 over tau 1s plus 1, and this is some kind of a time constant that defines how much filtering you want to do. The derivative is simply s, right? Same another first order filter right here with a different time constant, and you obtain velocity in the s domain, derive the velocity, and then obtain acceleration and filtered out acceleration right here. Okay, so the overall transfer function, and once you're in the Laplace or the s domain, all you have to do is multiply all of these to get the overall transfer function. So here's the overall transfer function between the acceleration signal that I obtained at the end and the initial raw data function. So the A of s over R of s is the transfer function, and it's s squared, so the two s's right here, divided by tau 1s plus 1 times tau 2s plus 1 times tau 3s plus 1. So as I indicated in the previous video, the nice thing about this is that it's a polynomial over another polynomial. So those are relatively easy to find, to work with, and you can find the roots. So the roots of the numerator here are referred to as zeros. And if I plot the root on a complex plane, so on the y-axis here you have the imaginary axis that represents frequency, and the real axis is here. All the poles and the zeros are real numbers. In this case, they're not complex numbers. So you have two zeros that comes from the s here. So that's, if you try to zero out, look at the root of this polynomial, s squared is 0. 0 times 0 equals 0. So the two zeros are here. And the roots down there, well, you don't have to multiply the polynomial. You already have the answer. So it's if s is minus 1 over tau 1, this is equal to 0. So here's the first pole, and those are called poles, second and third pole. So looking at the frequency response for such a pole zero diagram here is intuitive. It's relatively easy. All you have to do is go along the frequency axis here and look at the ratio of the length of the zeros versus the length of the poles. Alright, and that'll give you an order of magnitude. So as you're very close to 0 here in the frequency, so this is 0 frequency right here, you see that the zeros dominate, and because there's two double zeros right there coming from the derivative, as I mentioned, they tend to amplify frequency, and that's the amplification that you see right there. Right, so this is the frequency amplification that you see, and 1 0 is 20 dB per decade, so you have 40 dB increase right there. Eventually, you hit the first pole at that frequency, which is angular frequency of 1 over T1, so more or less right around here, right? This pole here starts to cancel out one of the 0, and the canceling out, gives you like a 20 dB per decade if you want a new slope. The second frequency is 1 over tau 2, so you're up here, so this is tau 2, and you're more or less up here in the frequency axis, and then the second pole here starts to cancel out the zeros, and this is where you get this sort of like flat response. And finally, there is one additional pole compared to the numbers of zeros, so eventually that third pole will come to dominate in much higher frequency. So when you're way up there in the frequency range, what do you see down there? You see 3 poles, and these poles are dragging down the frequency response while these zeros are trying to lift it up, but you have 3 against 1. So this third one is basically starting to act up like if it was all by itself and bringing the frequency down. And this is, the reason why all in all, I'm getting some kind of a filtering on the overall signal. Where do I get acceleration? I get acceleration from doing the double derivative, and I'm taking out the high frequency noise using these 3 poles using the filter. Right, so it kind of nicely adds up, and this is the overall frequency response of the filter that I use. Alright, so this could be a blast from the past for some of you, and for others, probably have no clue what I'm talking about. That's okay. Alright, enjoy.